Greetings. Welcome to section 3 of chapter 17 on hearing and music. In section 2, we focused on the frequency of what you could hear. In section 3, we're going to focus on sound intensity, or really how loud is it. So hearing threshold for most humans is about 1 times 10 to the minus 12 watts per meter squared. This is given the symbol I naught or I sub O for being the lowest intensity that most people can hear. On the other extreme, we have a jet plane. That has an intensity of about 100 watts per meter squared. This is a huge range. To give you a perspective, the atomic nucleus is about 10 to the minus 15 meters. The atom is about 10 to the minus 10 meters, and a football field is about 109 meters. So notice we're going from something the size of a nucleus or an atom to something the size of a football field, but in sound intensity instead of in length, right? It's a huge range, okay? Because it is a huge range, this makes the numbers very hard to work with. So physicists take a step to make it easier, and then that step that they take involves logarithms. So just a couple reminders of logarithms. So first, why are they nice? Well, if I have the log of 10 to the minus 10, that answer is minus 10. And if I have the log of 10 to the minus 6, that answer is minus 6. The log of 10 to the 0 is 0. The log of 10 to the 2 is 2. So you can see I've taken some range that goes from 10 to the minus 10 to 10 squared and reduced it down to a range from minus 10 to 2. It's much easier to work with now. Now, if you're going to work with logarithms, you need to have some understanding of how logarithms work. So I have a couple of useful pieces here. This one, x equals log y, corresponds to y equaling 10 to the x. That is the definition of the logarithm. Okay? That's just the definition. This down here is one of the properties of logarithms. So if I subtract logarithms, log of a minus log of b is the log of a divided by b. And you will need both of these when working problems in this section. Okay? So, how do we make use of logarithms? What we do is we redefine the intensity. Instead of writing it as an I, what we do is we say it's beta. Why beta? Because we're physicists and that's what we do. Right? The units here are dB, so this whole thing is telling you, hey, it's sound intensity in dB. Normally, physicists don't write out what the units are with the variable, but for this equation, they do. I'm not 100% sure why. Sorry. Okay, so the intensity in dB is 10 times the logarithm of the intensity divided by the threshold intensity. Remember that threshold is our 10 to the minus 12 watts per meter squared from the previous slide. Okay. Now let's put this into perspective a little bit more. Here is a table from your book. Right. So the intensity of the hearing threshold, remember, is 10 to the minus 12 watts per meter squared. That's this number up here. In dB, that number is 0. And then I go up in intensity as I go down. So a quiet home is 10 to the minus 9 watts per meter squared, which corresponds to 30 dB. Okay. A classroom lecture, which we all wish we were doing, is about 10 to the minus 4 watts per meter squared, which is 80 dB. Our jet plane, remember that was 100 watts per meter squared, so 1 times 10 to the 2. That corresponds to 140 dB, right? Notice if you're near a jet plane at 30 meters, this will cause severe pain and damage to your ears in seconds, which is why you see the workers on the tarmac at the airports all wearing ear protection. If they didn't, they'd all be deaf, right? If we go up 2 more orders of magnitude to 10 to the 4th watts per meter squared, you just burst your eardrums at 160 dB. Let's avoid that, shall we? Okay. Now, I know that you're cringing at this point. Logarithms are not something that you have done in a very, very long time and you don't remember. The next 2 slides are examples of working with logarithms. Okay. So the first one, what happens if we double the intensity? What is the change in dB if we double the intensity? So for this, I'm going from 1 watt per meter squared to 2 watts per meter squared. But it doesn't matter. The answer would be the same if I was going from 10 to 20 or 50 to 100 watts per meter squared, as long as it's a factor of 2 here. Okay, so I'm wanting a change in dB. So I'm wanting a change, that's a delta beta in dB, right? And that's going to be my first sound, or I guess I want to do final minus initial. So that would be the sound at the doubled intensity. That is supposed to be a 2 and it's not writing. Okay, take 3 at writing a 2. There we go. Minus the original intensity. Okay, so here we will have 10 times the logarithm of 2 watts per meter squared divided by 10 to the minus 12 watts per meter squared, minus 10 times the logarithm of 1 watt per meter squared divided by 10 to the minus 12 watts per meter squared. Okay, I'm going to factor out a factor of 10 because I got it in both pieces. So now I have the log of 2 watts per meter squared over 10 to the minus 12 watts per meter squared minus the log of 1 watt per meter squared over 10 to the minus 12 watts per meter squared. And you can see here, I'm subtracting logarithms. If I go back a couple slides, I can make use of this example. Log A minus log B is the log of the difference. So plugging that in is 10 times the log of 2 watts per meter squared over 10 to the minus 12 watts per meter squared, all divided by 1 watts per meter squared over 10 to the minus 12 watts per meter squared. Believe it or not, this all simplifies down to 10 times the log of 2 watts per meter squared over 1 watts per meter squared. Okay, so remember we got denominator here, that cancels with this guy. If you want, you can work with it as an improper fraction and that would flip up to the top when you make it a proper fraction. Right, so I'm left with that. I can now see why it wouldn't matter if I had 2 over 1 or 100 over 50, because I end up with a ratio. And 100 over 50 will reduce to 2 over 1. Okay, at this point, I can plug this into my calculator. 10 times the logarithm of 2, I'll put the divided by 1 in, even though it's not really needed. And I get an answer that this change in intensity is 3.01 dB. So if I double the intensity, that corresponds to a change of 3 dB. Okay. For the next example, we're going to do it the other way around. If the intensity of a sound is 64 dB, what is the intensity in watts per meter squared? So I'm going to pull out my formula. Beta in dB is 10 times the logarithm of I over I naught. And now I can plug in. I'm told I have a sound of 64 dB. And that's 10 times the logarithm of the intensity I want to know, divided by the threshold intensity, which is 10 to the minus 12 watts per meter squared. Okay. So to solve this, the first thing I need to do is divide by 10. So I get 6.4 equals the log of I over 10 to the minus 12 watts per meter squared. And now I need to flip backwards again to this formula now. So if x equals log y, y equals 10 to the x. Okay, so if x equals log y, then y, which is I over, oops, that's not a 10 to the minus 12. Let's see if we can erase with, we're just going to scratch out. We all know how well erasing works with this. I over 10 to the minus 12 watts per meter squared equals, okay, so if x equals log y, y equals 10 to the x. So that would be 10 to the 6.4. In which case, I equals 10 to the minus 12 watts per meter squared times 10 to the 6.4. And if you put that into your calculator, 10 raised to the negative 12 times 10 raised to the 6.4, you get an intensity of 2.5 times 10 to the minus 6 watts per meter squared. Now let's just check and make sure that that makes sense. If we look here, we had a number of 64 dB, which is between 60 and 70. On our chart, that tells us it should be between 1 times 10 to the minus 6 and 1 times 10 to the minus 5 in watts per meter squared, and the number we got was 2.5 times 10 to the minus 6 watts per meter squared. So yes, that did give us the correct answer. This concludes section 3.